Morning, everyone. Our first talk is by Tomas Ros. Thomas investigates EEG neurofeedback as a tool to help treat brain disorders. He completed undergrad studies in physics, master's in neuroscience, PhD in psychology, so he's very interdisciplinary. He's currently a postdoctoral fellow at the Department of Basic Neurosciences in the University of Geneva, Switzerland. Thomas.
So good morning, everybody. Thank you for the invitation, first of all, from the organizers. It's a pleasure to be here. So we'll start a little bit with some theory as a base. Let's see how far we get. I will be mainly talking about EEG oscillations. So you can see here, in terms of the full spectrum of where we can intervene in the brain, the oscillations, brain oscillations, where mostly neurofeedback is done, is here at this level of the network level, and that's also where the brain stimulation occurs. On the other hand, when you have medications, the sort of older approaches, they act here at the lower levels, where on the synapses. So, and I know a lot of the talk today will be about fMRI neurofeedback. And I just wanted to show that there is a connection between oscillations and metabolism in the brain. So my talk will be about EEG oscillations and mainly the amplitude of those oscillations. But you can see here that there is a clear link between the electrodes, where they're placed, and the metabolic activity. So for the low frequencies that occur around up to from 1 to 20 hertz, those are negatively correlated with the bold signal. So you have a higher metabolism with lower amplitude of the low frequencies. And inversely, with the gamma frequencies, you have a higher metabolism, so there's a positive correlation. So just bear in mind when you're looking at the next slides. Okay, so how are oscillations generated? Essentially, you have the synapses here that fire, and the ionic channels that are opened, they create a depolarization that creates a voltage change. And essentially, you have these synapses and neurons firing, and when they're firing out of sync, so individually and independently from each other, then you have a very small signal, right? So because each one is firing small, and then you're recording it on the scalp. And it's the same thing for the bold signal. Essentially, it's a metabolic activity that's required for the neural processing. The microphone doesn't work very well, sorry. So essentially what I want to show you also is that when these synapses fire more together in sync, you have a higher amplitude oscillations. So there is an example there that you can see, and it's the same again with the bold signal. So what are we measuring in EEG? You're measuring, actually, each one of these traces is an EEG channel. This is how they're set up. And we can look at over two different sort of domains, the time domain and the amplitude domain. So the amplitude is simply the y-axis, and the time domain is the frequency, how closely spaced are the peaks. So you can see here, there's different frequencies, they're jumbled up together, and there's different amplitudes that occur in time. So how are they related? Essentially, as I showed you, those neuronal activities, when synapses are firing together, and let's consider two synapses or two neurons, that would be the black and the orange trace. When they fire together, as I showed you before, when they're in phase, they create a large amplitude, which is that purple. Okay, so the purple goes up. When they're in phase, it's constructive and destructive interference that you should know from your physics class. Exactly here. And so when you have a high amplitude of the EEG, that means that the neurons are simply firing together. Okay, and essentially that means that the amplitude of the EEG signal is a good indicator of local synaptic coherence, okay? Local synaptic connectivity. Synchronization is the word. So you can then decompose these signals, throw away the time and just summarize it as a spectral plot. So you have frequency here and how much activity of a particular signal you have in a different frequency band. So this is the general profile for a resting state EEG, where the largest activity, the highest amplitude and synchronization occurs in the alpha band. You see this yellow band here. Okay? So the point is how can we use these different synchronization patterns to identify patients and maybe also use them for treatment? Now, here you have a summary plot of some of these spectra in psychiatric disorders. And you can see here clearly that as an average of all these psychiatric disorders, there's a very big difference between the amount of synchronization that occurs in the slower frequencies, i.e. it's much higher, okay, in the patients. And also in these faster bands, there's also much higher. And then there's individual signatures for these patient groups. And if we take one example of obsessive-compulsive disorder, not only are the frequencies different and the amplitudes, but also the location of these sort of abnormal activity is different in the brain. So they have a localized, area where they are different. So in this case, in healthy controls, theta has the highest power amplitude here in the occipital areas, but in obsessive-compulsive disorder, actually, this becomes the largest theta generator. Okay. So, one more slide about how synchronization is related to behavior and processing. Well, we know that abnormal synchronization is associated with brain disorders, but also it can lead to completely behavioral changes in a healthy subject. So, for example, when we give you the propofol, which is an anesthetic, there's an increase in this alpha amplitude in the frontal lobe, and that leads to unconsciousness. And as soon as you have a return of consciousness here, ROC, this alpha amplitude increased synchronization is released. Okay. So this is going to be one example of a disorder that I'll talk about more in detail. ADHD, it's one that the neurofeedback has been used for the most. It's one of the earliest clinical disorders that neurofeedback has been used for, and especially EEG neurofeedback. And what you can see here is, again, these frequencies plots, and essentially these synchronization patterns, i.e. the amplitudes, are consistently higher in ADHD than in controls, in healthy subjects. So you can see here for children, the delta band as well as the theta band is higher than in healthy children. But then as you develop, these bands decrease in amplitude, but consistently the ADHD profile is higher. So that goes to show that there is a developmental change with the disorder, but it's consistently not in line with normal development. So if we know that there is this abnormality, what can we do in neurofeedback? Well, this is one of the largest neurofeedback studies that have been done in 2009, and it's a randomized controlled trial. And what they found was that when they applied neurofeedback to downregulate this theta amplitude, so this band here that you can see, theta, this increase here, essentially what they did with neurofeedback was to decrease this, to train to downregulate, so that means suppress and come here to this kind of normative spectrum. What they found is that, in fact, that's correlated to their ADHD score change afterwards. Okay? So there are inter-individual differences, and those who decrease the theta the most in the resting state, not during training, but those that translate into resting state change, have the best improvement in ADHD symptoms. So there is a causality there between what parameters you train in the brain and what the behavioral outcome. So how can we explain this maybe in terms of why these synchronization patterns relate to behavior, and how by normalizing them we can have improvement in behavior? Well, there's one theory that's the complexity theory that says that you have a sort of maximal complexity in between two extremes of order and disorder. And disorder you can class as the elements are independent from each other, like a gas or a white noise signal. And then you have order, which is a crystal lattice or any kind of orderly solid that everything is coupled to everything else. And in between is where kind of all the fun happens, the biological life that is alive. So I'll try to relate what we mean by order disorder. So here is synchronization. I start with a definition of synchronization. I showed you earlier that it means synapses firing together. You can see that syn chronos in time, and this would be in phase and out of phase. And in fact, for synchronization to emerge, you need to have coupling between those independent elements. Okay? So you can see here there's a coupling there, and I'll show you a brief video. Hopefully it works. Okay, good. So these are metronomes, and at the moment they're firing, they're out of phase completely, randomly, and they're not coupled to each other, okay? You can hear the clicks. Now they're going to introduce coupling because the board is moving and they can move, transfer energy to each other. Okay? So they're a little bit out of phase still. If we wait a little bit longer, they're going to start going in sync. There. Okay? So I hope that's a good demonstration of what we mean by synchronization and coupling. And so, in effect, we can actually equate this order-disorder x-axis with synchronization itself, which means that if there's increased coupling, there's more order and also more synchronization, and decreased coupling, lower order, and lower synchronization. And this is a paper by Toroni that proposed this link between complexity and synchronization or coherence. So they have done some studies where they simulated, the coupling and what kind of dynamics you can see. So this is the coupling that you would have in the brain if the local connections were only coupled, okay? Just like in a gas, you would have only, well, even less in a gas, but you have very small coupling only locally, and there's no long-range connections in the brain. So this is the kind of pattern you generate dynamically. And you can see they're just little blobs. It looks like a gas. It's very disorderly. There's not very much complexity going on there, apart from it has high entropy, but it's pretty random. So now it's what happens if we couple everything to everything, okay? So you would expect that you would have higher synchronization. So what exactly does it look like if you have, completely all-to-all coupling? And you can see it's exactly like the metronomes. Everything fires at once and stops firing at once. Okay, so then we try the intermediate scenario, where it's so-called small world connectivity, where some things are locally coupled and then there's a few long-range connections. It's like road or airplane networks, okay, hubs and so on, and the kind of dynamic you get from that. And here is the so-called complex dynamics, which is large changes, bigger blobs, and they're more correlated in time and space. But there's no general sort of formula for this kind of activity. And this is exactly what happens in the brain. So it's possible that, when we try to normalize the synchronization levels, we achieve this state where the complexity is highest or these kind of patterns emerge, okay? And that's maybe very important for information processing. Shift F5. So, next one. So what can we do about these patterns, and how can we, translate these complex patterns into some clarity and see whether they're related to behavior? So in essence, this is the theory of self-organized criticality. So the theory of self-organized criticality says that for biological systems, that actually the system tunes by itself to this region where the complexity is the highest, and that also the synchronization levels occur in this intermediate zone. You see there, it's called the critical region. So this critical region is basically the region where you have the optimal information processing, the optimal dynamic range, and all those memory as well. So all the parameters that are required for good information processing in the brain. And the reason why it's self-organized is because the system tunes by itself to this sort of optimal level. The thing is that the background behind criticality research started with thermodynamics, and that showed that you can actually tune particular systems manually to these different complexity patterns, but it would not obviously able to self-tune itself. So I have an example for you of a physical system where you have criticality, okay? So in this system, this is called an Ising model, and it's actually the background behind how magnets become magnetized. And essentially what happens is, I told you that the criticality occurs at the phase transition between order and disorder. Okay? So in this magnet, there are electron spins that either point upwards or downwards. Upwards would be red, downwards would be black. And they entrain each other also. They kind of synchronize, they're coupled together. But the coupling is dependent on the temperature. If you increase temperature, you add energy into the system, you add randomness into the system, and therefore the coupling becomes lower and the magnetization becomes lower. Okay? But if you start to drop the temperature down, the magnet becomes more magnetizable. And these are these domains that occur. They're similar to those patterns that I showed you with the sphere. They become larger and larger until the magnet becomes one black thing that is one whole magnetized, everybody magnetized in the same direction. And here is a plot for that. So you have T is the real temperature and TC is the critical temperature. And when the real temperature occurs at this ratio of 1, then you have this so-called phase transition, where the critical region, which is defined as the critical region, and there you have the maximal complexity, okay? So how can we sort of look at that also in... I have a demo for you of what that looks like. So this would be here you see here on the left, on the right, oops, T over TC, that's the ratio. This is the very high temperature. So the temperature is 4 times higher than the critical temperature. Okay, and you can see that there's almost random noise there. So that's the disorder that you're looking at here. And this is each of these black and white dots is basically the electron spin. So it's the domain. And what happens if you then start to drop it close to the critical temperature? So we're going down to 1, to this phase transition. You see now the patterns become a little bit more patchy. And as you reach 1, okay, we're beyond 1, you get to this special region, which is around 1, where the patches become very complex, and there is no general rule, and they're shifting, and they're correlated across time and space. Okay? And then as you go even lower from that, so you leave this critical region, you get this. Okay? So you get nothing. You get, again, just everybody pointing in the same direction. So you lose complexity. All right, so how can we mathematically sort of harness these different patterns? How can we define them? And one way is to use the correlation over distance, so over different scales. And here it's called a dynamic correlation, and that's basically the co-fluctuation of these blobs, like black and white, over distance. And so at the critical temperature, as I showed you, these blobs are larger and they extend more in space. Okay, and at the high and low, at the high and low temperatures, the dynamic correlations actually extinguish themselves. So firstly, in the low temperature, they extinguish because there is no fluctuation at all, so the dynamic correlation is 0. And at high temperatures, the fluctuations are too random, and the blob size is very small. So the drop-off of the correlations across distance is smaller, okay? So this is one of the defining characteristics of a critical state, is that it has this high correlation over scale, over time, over space here. And this is, sorry. I think it's here. No, there was another graph that showed that that's maximized at the critical temperature. So I showed you an example of a critical system in space, okay? Now we could translate the same thing in time. And that's when we have time series. And time series can occur at many different scales. So, for example, here, this is the heart rate time series over 300 minutes. This is what the time series looks like. And then as you zoom in, you go into 3 minutes, it looks similar. And then you zoom in again at even less, 30 minutes, and then 3 minutes, it looks self-similar. And this is, if you zoom in into these time series, you can see there's kind of no never-ending. And that's called a scale-free system, which means that it has a similar properties at different scales. Okay. So one model that you can use to analyze this kind of system is called a random walk model. So here you have, this is basically what would be the trajectory of a molecule if it occurred in a gas, okay? So let's say the molecule is the red one, and it's moving randomly across space. And when the system is completely random, this is the sort of random trajectories it generates. And that's the random walk, okay? So how can we use that for brain activity? So I'll just show you what a random walk again looks like. I like to do demos so people understand how it works. This is a demo in Excel what a random walk consists of. You start with the 0, 0, which is basically the origin, and then at that origin you add a random sort of generator. So here would be the rand function of Excel. And here I've subtracted minus 0.5 so that it's centered around 0, because usually the rand function goes from 0 to 1. And then you add that random number to the previous number. So it's a cumulative walk. It's randomly, it's like as if I blindfolded you, what would you do if you didn't know where you were going? But you accumulate from position to position. And so that's what I filled down the same formula. And if we go all the way down and take all these time points in this random walk, okay, and then I click the graph. So this is what a random walk looks like. So you start here at 0, and then you go around. That's what the molecule does. So how is this related to time series? Well, you can use the same model and just take one axis. So I'm not looking at both x and y, I'm just looking at x. And then you do the same thing. And that's your time series of the random walk. Okay? It's a cumulative time series, and you can use that as a model for the time series that you have in the EEG or the bolt signal. So what are the properties of this cumulative walk? Well, essentially, here's time. So instead of distance, this is time now. And this is the amount of fluctuation occurring when the random walk occurs, right? And you can see that the variance of the random walk as you accumulate time increases in this logarithmic, in a power law fashion, okay? So you can use that as a property to look at different types of random walk. And in this case, if the random walk is completely noisy, that means Gaussian or Brownian, then this, the standard deviation of the random walk increases with a particular exponent here, okay? It's a power law, and the exponent is actually a half, okay? So that would be the statistical signature of the scale-free system. And when you plot that, you see here y equals x to the 0.5. So it's a root of x, is the white noise signal. But the question is, what about different types of random walk? What if there's random walks that have an exponent that is larger, so the variability, the standard deviation increases with time even more than a white noise signal, or decreases with time relative to the white noise signal? And that's how you can then start to define these different exponents with this model. And this is so-called the Hurst exponent. So you see here, this is the equation. This is h, which is the 0.5 here, okay? And this is time, and this is the standard deviation. And if you take a log of this equation, it's pretty simple, then you can have a linear model where h, the gradient of this function, determines this exponent, okay? So h is simply the exponent of these different random walks. And so when you do a linear log-log plot, that's what you get. You have an h of 0.5, that's a gradient of 0.5, a gradient of 0.7, and a gradient of 0.3. So what does actually that mean in real life? I mean, 0.5. So we know that's a white noise signal. That's when it's a Brownian. And this is how the cumulative look looks like. When it's 0.5, it looks like this. It has an intermediate variance. When it's 0.7, the variance is much larger. And when it's 0.3, the variance is very small. So what does this mean in real life? Well, essentially, these are different types of walkers that occur, okay? So this is the middle one, a 0.5. This is the random walker. I told you it's as if I blindfolded you. You have a certain pattern, but there's no coupling. There's no dependence between the next step you take and the one after. Now, there's the anti-correlated coupling, where you sort of compensate for going left and then go suddenly right. And that's more like how a penguin walks. Okay, and the signal does the same. The system is up and down. And then there's the sort of the drunken Santa. He goes in one direction and goes there for a long time and then starts to autocorrect afterwards when he realizes it's a bit late. So he accumulates more variance. So you can look at this brain signals, and this is now where we come finally to the meat of the issue. You can look at the signal of the EEG, and you take the amplitude of that signal, and you treat it as one of these walkers, okay? And you find out what kind of walker is it. Is it a random walker, or is it a sort of a Santa, or is it a penguin? And essentially, you see here the electrodes, the values are 0.7, 0.7, much higher than 0.5. So it's not a random system. So essentially in the brain, the signals that it generates are sort of, more like a Santa. So if you look at these H indices, so you have this index, which is called an H index, and an H exponent, a Hurst exponent, and you have correlations genetic correlations between twins, that these exponents are conserved. And also here, when there's dizygotic twins, it's not conserved, and these exponents increase with age. So you see here at 5 years old, they start at about 6.5, and then they increase in magnitude as you age. So it's typical of development for these exponents to become maximal after some time. I have to go quickly because I don't have much time left. So how does this relate to brain activity and brain disorders? Essentially, this exponent gives us additional information that we don't have in the amplitude spectrum. Okay, so the amplitude spectrum is basically our synchronization, the x-axis. Now we're starting to look at the complexity of the system, which is the y-axis. So here you have the exponent. You see the exponents are lower in Alzheimer's patients. They become more random than in healthy controls in the alpha band, and the amplitude is actually not significantly different. So the exponent tells you an additional amount of information that the synchronization of the system cannot or does not. And it's the same thing for major depressive disorder. Sorry. Here, the major depressive disorder in theta band, the patients have a lower exponent than the controls, and in fact, this is correlated with their clinical score. So the more depressed, the lower the exponent. Okay? And it's not the case as much, although the synchronization can predict also, but not as nicely as this complexity exponent. And finally, for the fMRI people among you, you can do the same thing on the fMRI time series. So you have the time series and you calculate this Hurst exponent. And in fact, in autism, this Hurst exponent is closer to white noise. So white noise exponent is 0.5, as we've said. This autism spectrum disorder exponent is 0.57, and in a healthy subject, it's 0.88. And it's particular to particular regions. These are the regions that are most affected, where the signal is the most random. So finally, how can we use this information to illuminate maybe neurofeedback mechanisms? So we did a study, and we subjected subjects to alpha desynchronization training. So we went straight for the synchronization because that's a measure you can do in real time. This Hurst exponent, as you saw, it's scale-free, so over time, you cannot really train that. But we wanted to look at, does neurofeedback affect the Hurst exponent? So we had 3 groups: healthy controls of 20, sham group of 20, where they had faked feedback, and a clinical group with PTSD, post-traumatic stress disorder. And then we just looked at the resting state activity 3 minutes before and 3 minutes after the neurofeedback, and see is there a change in this exponent before and after. And just to show you that for the training itself, people started here at rest, the amplitude was very high, and they trained to decrease the amplitude, and you can see it was successful for both the PTSD group and the neurofeedback group. But the sham group, it went down and then raised back up to normal levels, and the variability is very high here. So essentially, the neurofeedback intervention worked very well. You can see here the minimum where we fed back from. So that's just to show you that the neurofeedback worked. And then we calculated this Hurst exponent by calculating the gradient of this time versus fluctuation over different time scales from 1 second to 30 seconds. And these are the alpha bursts you can see here. So these are the alpha amplitudes that we fit these plots to. What did we find? So we found that alpha amplitude, interestingly, doesn't change pre to post neurofeedback, although we trained the alpha amplitude down. in the healthy controls. And if we then look at the Hurst exponent, interestingly, there's a change. And there's a boost in the Hurst exponent after neurofeedback, and only in the neurofeedback group. And it goes from about 0.7 to 0.75. So there's an increase in this complexity measure. And then what happened in the PTSD group? Well, in PTSD, you can see in alpha amplitude, there's an increase in alpha, even though there's a decrease during training. So that's a so-called rebound homeostatic effect. We'll get to that later. But interestingly, you can see that already compared to the controls, this PTSD group is lower in alpha amplitude. And then after neurofeedback, this alpha amplitude gets normalized. So you see here, PTSD T1 to T2, there's a boost around these regions. And in fact, it's the same area where these controls have the higher alpha. Okay? But what happened to the Hurst exponent? Also similar dynamic. The Hurst exponent is normalized and is lower in PTSD than controls. So Hurst exponent is more random, and then post-neurofeedback, it's normalized almost consistently across the scalp, especially in these midline regions here. I realized, yeah. It's almost there. So, can we get additional information by using this complexity measure? Well, we found that actually it can be a good predictor, like the other papers have shown, of a relationship with behavior and sort of clinical self-report. So the more these patients, so we gave them a questionnaire before and after the neurofeedback session. This is just one session, by the way, so it's pretty impressive that this can happen in the brain, especially in a clinical population. But the more the Hurst exponent increases post-neurofeedback, this is the change, the greater the decrease in arousal symptoms. Okay? So it seems like by changing the complexity of the brain and normalizing it, there's an improvement in effective function. We plotted all the points then in this y-x-axis that I showed you before, where we had order, disorder here at the bottom, and we had complexity here at the top on the y-axis. And now we plotted all the points pre and post neurofeedback. This is not change. This is just individual points pre and post neurofeedback for all the different groups: eyes closed, controls, PTSD, neurofeedback, and sham. And what did we find? We found this inverse U-curve, just like you would expect from the self-criticality model. Okay? And so there's a maximal, so just to summarize, there's a maximal complexity in this middle intermediate region of alpha synchronization, and the PTSDs are down here, and then they went up here. So that's exactly what I was just talking about. So essentially, you have a critical region, PTSD starts off more random, more disordered, and neurofeedback normalizes it. And I showed you in ADHD before that synchronization is too high, and then when you decrease synchronization, the symptoms improve. So this model would potentially predict that ADHD go from this side here, where it's also suboptimal, towards the critical region. We don't know, there are no studies with Hurst exponent in ADHD, but it would be very nice to see what happens if that model is predictive of that. And finally, just to show you that the brain does this kind of self-tuning on its own all the time in healthy subjects. In fact, oscillations, synchronization changes across the sleep-wake cycle. Here, this is in the morning and in the evening. So when you're in the evening, you accumulate synchronization, you accumulate order across the whole band, across the whole EEG range. And then when you wake up, due to synaptic plasticity and homeostasis during sleep, you actually downscale these this two orderly pattern. So it seems like maybe the brain is seeking this more lower synchronization level, which is within the critical region. And this is actually some of Orem's work as well, that show that with sleep deprivation, if you look at theta band spectral power, you start to accumulate power with time, as you can see here. And then once you go to sleep, when you wake up the next day, it gets back to the beginning, okay? So the model shows that maybe that criticality is restored. And this is our paper that we've tried to explain how this works, sort of as general theory. And one of the ideas is that these patients reach a local minimum where they're stuck in their sort of non-critical state, and it's because of maladaptive plasticity. And then if you try to normalize it by doing neurofeedback, then they can finally go back to the critical state on their own. And that's it. Thanks very much for the time.
questions from someone? הנה, יש שם שאלה.
Correct. Very, very good question, because obviously it's not one fixed point, and they say that's why they say it's a critical region. And obviously, during tasks, the exponent goes to 0.5, and in other cases, it can even go higher. The way we think about this is that actually it's about a dynamic range. So if you're in the middle, you can visit both the higher complexity, sort of the highest synchronization and lowest synchronization. If you're stuck on one or the other side, then your range is different, right? You're not poised in the middle. So that's maybe why this middle region, this middle synchronization is healthy for people. Also, you can imagine that at that level there's the highest complexity, which is what the brain can generate the largest dynamic repertoire. So it's more like the most creative state. But it doesn't necessarily mean that that particular number is sort of is beneficial for any type of brain state. What we're talking about is that it's for the resting state from which the brain then departs towards more randomness or less randomness. Yes.
How did you apply sham neurofeedback?
So sham neurofeedback, we took a representative subject of the real neurofeedback group, where basically the reward was, consistent with a good neurofeedback performance, and we took that EEG and we replayed it to the sham participant. Okay, without.
You get them a different brain thing.
Exactly, without them knowing, and also without any contingency between their real brain activity and the activity that's being replayed, obviously. Yeah.
Okay, one last question, Asaf?
Yes.
Have you looked at different measures of complexity, like multi-entropy or?
It's a good question, yes. Actually, we haven't yet. This was one model that we first looked at, but there are other models exactly that multiscale entropy is a very good one. And it will be interesting to see either on this data or future data sets whether this complexity. So essentially, the model of self-organized criticality says that complexity would be maximized, but complexity not in the effective complexity sense of what you're talking about, the multi-scale aspect, not the simple entropy aspect.
Okay, let's thank the speaker again.
Thank you.